Okay, my name is Dylan Watson on your kit. Obviously, you know because you're the one who got the email, Dr. Roby. So, what my extra credit is about is section 9.5, the alternating series. So, we know the definition of the alternating series is one, it says right here, an alternating series is one in which the terms alternate in sign, positive, negative, positive, negative. So, for example, we got plus 1, minus 2, plus 3, minus 4, plus whatever, right? That's an alternating series. We know that's what it is. Ooh. Right? We know what that is. So, for example, we have the infinite series when n equals 1, the negative 1 to the n plus 1 power over n. Now, we know that it's considered alternating because of this right here. This is what gives it away. This is what shows you, hey, it's alternating. So, to write out the series, first 4 terms equals what? Negative 1 to the second power, because we do 1 plus 1 is 2 over 1, right? And then we do minus, let's back it up here, we know 1 plus 1 is 2, negative 1 squared is 1, so we'll write it like that, okay? So we know it alternates, so we write minus next. Negative 1 to the 2 plus 1 is negative 1 to the 3, which shows minus 1. And we know our n value is 2 because that's the next one. And then we continue this pattern. Plus 1 over 3, because when n equals 3, 3 plus 1 is 4, negative 1 to the 4th power is positive 1. And then for the next term is going to be negative 1 over 4. That's what an alternating series is going to technically look like, okay? So here it is. This is the alternating series test. Now this test only tests for a sub n, regular a sub n. This test only works with regular a sub n. That is, sorry. And so this test, we know the series of a sub n converges if the limit n approaches infinity, the absolute value of this equals 0, and the absolute value of the series is decreasing for all n greater than or equal to some integer n. So basically, if it's decreasing. So decreasing, and this. Again, only tests a sub n, not absolute value of a sub n. Okay? So, okay, so in this example, we have to show whether it converges or diverges with this. So, so let us take the limit as n approaches infinity. The absolute value of this all over n is equal to limit over n. Nope, wait, hold on a sec. Not limit to n. Limit as n approaches infinity is 1 over n. Remember, this test for regular a sub n. You'll know why in a second. So we have that. And so what is the limit of this? Well, equals 0, because a constant over something increasing will always end up being 0. So, let's see. So that's one part of the test. The second part of the test determines if it's decreasing. So we know that it's the a sub n in absolute value equals 1 over n. This is decreasing because this is constant over increasing. Okay? Which equals, I like to say, which ends up being decreasing. Okay? Decreasing. Constant over something increasing ends up being decreasing. So we write out come on. Okay. We write out this series converges by alternating, I'm going to put alt for short, alternating series tests. Okay. The series converges by alternating series tests. Ooh, you know what? Maybe I should just make this a little smaller. Okay. Cool. So that's example 1. In example 2, it's a little different. Okay. But same steps. We know, let's take the limit of a sub n, which is this part of the series. We take the limit of n approaches infinity, the absolute value of this. Remember, this only tests for the regular a sub n. Okay? Right? This ends up being limit as n approaches infinity. It is n over 2n plus 1. Now, when we take the limit of this series ends up being something very nice. This limit ends up being very nice because of the RFLT, also known as the rational function limit theorem. Basically, you take the highest degree powers and you take the coefficients. So the limit ends up being 1 over 2. Now this fails because it's not 0. And because this is not 0, the test fails. Remember, this is the series a sub n, regular a sub n in absolute values, but it's not the absolute value of a sub n. Remember, this is what we're looking for. Equals 0. That's a good. But because it ends up being 1 over 2, this does not converge. So we say test fails. Test fails because the limit n approaches infinity. A sub n does not equal 0. So we say series diverges by series diverges by divergence test. Now, the divergence test is when the limit n approaches infinity, a sub n does not equal 0. That's when you know it diverges. So, it's a little, good thing to know. Now remember earlier when I was talking about how the alternating series test for this regular a sub n, right here, regular a sub n, correct? Now, when we do these, checklists, this limit right here, you're taking the absolute value of this, and you're putting this inside absolute values. This does not mean its absolute value. As you can see right here, we know the series absolutely converges when the series in absolute value converges, which means you have to take the series, make it absolute value, and then you have to do a different test. Because when you use the alternating series test, you're only testing for regular a sub n, not the absolute value a sub n. So we highlight this so we know. And the series absolutely convergent. It absolutely converges when the whole series converges. This absolute value. We say it is conditionally convergent when the regular a sub n converges, but when you put it in absolute value, it diverges. So, for instance, this was regular a sub n. That was divergent. But if we were to put this in absolute value, or how do you say this? If we were to put this in absolute value, right? Take the absolute value and do a different test. If we take the limit of it, we would know it converges absolutely. So we can take this definition of absolutely convergent and check if this absolutely converges. And we know it absolutely converges because, as we can see, if we took the absolute value of it, it would end up being this. And if we do the divergence test, we know the divergence test fails because it equals 0. Because we also knew this converges. So, in other words, always start checking for divergence or convergence by taking the absolute value of the series first. Just remember that. And it says right here, absolute convergence theorem. If the series absolute value a sub n converges, then the series regular a sub n converges. So basically, if this converges, if the absolute value converges, regular converges. Okay? Yeah, this is a motivating example, but we already talked about it, so we'll skip that for now. Just know that these this is like something you want to remember. If the absolute value converges, then the whole thing absolutely converges, aka this definition right here, that definition. But if the absolute value diverges, then you have to check the regular one, see if that converges. So remember, regular a sub n does not determine convergence. Absolute value does. So let's go to another example. Let's see. So in example 3 to 6, determine whether the series converges conditionally, absolutely, or just diverges. Oh, my notes. Okay, so we'll do an example here to prove that these convergence stuff works, the definitions. So we know a sub n, you know what, actually let me zoom in down here. Okay, whatever. We know the a sub n equals -1 negative 1 to the n power times n all over ln n plus 1. Okay? We know this. Let's take this in absolute value. The absolute value of this series is n to the ln power, not ln power, ln n plus 1. Oh, excuse me. We know that. So we can test for it divergence or convergence. Let's use the divergence test. So we take the limit. Why is it not working? Ah, there you go. N approaches infinity. And then this is absolute value, so this is okay. So we know this, right? Excuse me. Okay, so we know this is considered your absolute value, right? So if we take the limit of this does not approach 0. So because this doesn't approach 0, because this is growing and this is slower growing, this does not approach 0 just because ln is really slow and n is, it's growing. So the bigger this gets, this is going to end up being bigger than this, just because ln is really slow. So if we take the limit of that, we know it does not equal 0. Right? So we can determine that this diverges by the divergence test, but we can also take the limit of this and by L'Hopital's, because if you can see it, we know we got to use L'Hopital's. So we say we can only take L'Hopital's rule if it's a continuous function. So we say f of x equals x over ln of x plus 1. Right? But if we take the limit of that, it's going to be a little hard. So let's take L'Hopital's, right? Take the limit of m, x approaches infinity. We have 1 over x plus 1, right? Which ends up being, come on, work here. Okay. Which ends up being limit x approaches infinity of x plus 1. This ends up being infinity as well. So because we know this approaches infinity, because we know f of x approaches infinity, we know this will diverge because it goes to infinity as well. Okay? And so let's do another example, yeah? Maybe not this one. Let's do... let's see. No, this is good enough.